So, hi everyone. Welcome to Dear Lunch. Today we have Professor Dor Minzer from MIT to talk about recent developments in PCBs.
So thank you very much, and thank you all for coming. So I'm going to tell you about two recent results in PCPs. And I'm going to give you all of the proofs, all of the details. No, so I'm not going to do that. So I'm going to talk about work with my student Kai, about soundness and alphabet trade-off, and recent work with Mitali, Noam, and Nikhil, and also Jiwei Yan about quasi-linear PCPs. So let's get started. So what is PCP about? Well, one way to see it is about verifying computations. So let's say that you have some very complicated computation, which is depicted on the slide by a circuit, which looks kind of so I should okay. How about now? Okay. Okay. So I see this is a hard circuit also. So we have this hard circuit, and okay, now the clicker doesn't work. Okay. So this circuit has an input, which I'm going to call X. It goes through these wires and this and that, and at the end you get an output, which I'm calling Y. So how do you verify that C of X is equal to Y? So, of course, you can feed X yourself to the circuit, carry out the computation, and verify it, but this is as costly as computing the circuit itself, so giving you Y doesn't help. And verifying that a circuit outputs Y on a given input is something that appears all over the place, both in theory and practice, and this is a very fundamental task. And in complexity language, this is the class NP, but I'm not going to use this language too much. So here is a more precise definition of the problem. So what does it mean to verify? So to verify that XY is an input-output pair, I need to be able to provide to you a proof, which I'm going to denote by W, and sometimes I'm going to refer to it as a witness, that tells you that the circuit actually outputs Y when given X. So this is what verifying means. So what would be the most obvious witness? Well, I can just give you the configuration of the computation at each time of the computation, and you can just check that the initial configuration is the input X, and each step follows the circuit C. So that's clear, therefore there is a witness. But this witness is not very helpful because it's as expensive as computing yourself. So this is one witness, but in general, there will be other witnesses, and the two basic properties that you want are completeness and soundness. So by completeness, I mean that if XY is an input-output pair, then there is a witness that convinces the verifier, and otherwise, no witness is able to convince the verifier. So the three properties that I would like from our witness is properties that I'm going to refer to as locality, efficiency, and being short. So locality means that the verifier is only allowed to look at constantly many locations at the witness and decide based on that. So the verifier is going to choose a bunch of locations, let's say the ones that are marked in red, they're going to read them, and based on these values, they're going to decide whether to accept or reject. And maybe the verifier repeats it a handful of times, but after that, he wants to decide. So, this naive suggestion they said of just spelling out the configurations of the computation doesn't have this locality. It can be hardly called efficient, and it's also not short. So efficiency is something that I'm going to discuss a little bit later, but when I say short, I just mean that the length of W is not humongous. So the naive solution that we discussed, where you just output the entire computation, is none of this. And the first theorem, of classical complexity theory is by Cook and Levin, which said that there is another way to encode this witness, which at least guarantees locality. So at least locality is something that you have. So this is Cook-Levin classical theorem for the 70s. But now what about efficiency and shortness? Okay. So this whole talk is going to talk about can we do better? And I'm going to define what better means as we go. Okay. So one way that you can make it better is how many locations that the verifier read altogether. Because if you remember, the verifier reads 3 locations, then 3 other ones, but in total, maybe it will cover the entire witness, and then it's not really a fair game. But it turns out that you can come up with a witness where you don't have to look at all of the table. So this is another classical result called the PCP theorem, which we are going to also discuss, which tells us that you can achieve efficiency. And now I can tell you what efficiency is. Efficiency just means that in total, the verifier is looking at constantly many locations in the witness. Okay. Cool. Okay, so this is all of this stuff in picture views, but now let's move to the more standard language of computation and complexity, and I'm going to formulate things using the 3-sat language. So just that we're on the same page, a 3-sat formula is just a formula of this type that I wrote here. It's an AND of ORs. Each OR contains 3 literals, meaning variables and their negation. And the task is to decide whether phi is satisfiable or not. So with the 3-sat language, I can tell you truthfully what the Cook-Levin theorem says. It says that essentially this language 3-sat captures the entire class NP, which within it contains this verification task for every circuit C. And once you look at this 3-sat, the locality is already inherent because each clause involves only 3 variables. And this is indeed what I'm saying here on the slide. So, if I'm given a formula phi, what would be a witness that it is satisfiable? Well, I can just give you the assignment that satisfies it. And then to verify that it is indeed a satisfying assignment, I go over the clauses one by one. For each clause, I read 3 locations from the proof. I see that it satisfies. If it is, I'm happy. Cool. So as we refer to it as the previous slide, this is already a solution which is kind of nice. It's local. But it is not efficient because maybe my phi is not satisfiable, but I can find an assignment that satisfies all but one of the clauses. In that case, I would need to read many, many, many bits from the proof until I hit that one clause that is not satisfied. So it's not efficient. Cool. So towards stating the PCP theorem, let's look at the same very simple verifier, but let's take a randomized view on it. So what a verifier is going to do now, well, given a 3-sat formula phi, the witness is still a satisfying assignment. But now what the verifier is going to do is they are going to sample one of the clauses randomly and check whether that clause is satisfied or not. So now it is efficient in the sense that you only read one clause, but the performance of this is nothing to write home about. If phi is satisfiable, then of course the verifier always accepts. But if phi is not, then as we said, it may be a case that only one of the clauses fails. And in that case, you can only say that the verifier accepts with probability at most 1 minus 1 over the number of clauses. So it is local, but its performance is still quite awful. So can we come up with a randomized verifier which doesn't suffer these performance issues? Cool. So how do you improve that? So the way you improve that is you go fast forward to the 90s to the PCP theorem, which tells you, and this is now a big jump. It's not, I'm not going to be able to describe to you what the verifier is doing. It's taking half of a semester, roughly speaking. So it says that there exists a probabilistic verifier that I'm going to denote by VPCP, and some encoding of the witness, such that now the verifier looks at the proof. So the proof is going to be over some alphabet sigma. If you don't care about small lies, you can assume that sigma is 0, 1. But if you do, then think that it's alphabet size 5 or something like that. In any case, it's fine. So what a verifier is doing, they're sampling 2 locations in the witness, reading these 2 locations, and based on it, decide to accept or reject. And the performance of this verifier is the following thing. If I satisfiable, VPCP always accepts. And if phi is unsatisfiable, maybe it's barely unsatisfiable, still, even in that case, whatever witness you give me, the verifier still accepts with probability at most 0.99. So the point here is that 0.99 is a number strictly smaller than 1, bounded away from 1. So it's much, much better compared to the previous verifier. So that's the most important message of the theorem. And now let's look at some secondary considerations. Now, the witness that this theorem gives is slightly longer than the witness of the original verifier. But this is only a polynomial blow-up, so we consider that that's satisfactory for us. But other than that, this theorem is very nice. Okay. So as I said, you should think of the alphabet as 0, 1, but if it bothers you, then think about it as some other constant. And the length of the proof is polynomial, so done. We can move on to different things. Because we have locality, we have efficiency, and it's sound. And this is a very powerful result. Essentially, all of the hardest of approximation results that I know start from this theorem or some variants of it. So it's really, really fundamental. But once you prove some result, you can always try to improve it. So now we're going to squint at some things in this theorem and say, oh, I don't really like that parameter, can I improve it? And stuff along these lines. Okay. So that's the PCB theorem. So now let's squint at this theorem a little bit and try to see how much better can we hope the PCB theorem to be. And let me just say that there are more ways you can think of better PCB theorems than what I'm presenting in this talk. But these are 2 ways you can try to improve it. So first of all, you can hope for a better soundness. So now and henceforth, I'm going to refer to this acceptance probability in the case that phi is unsatisfiable as the soundness error of the verifier. So 0.99 is smaller than 1. It's nice, but you can hope for smaller numbers. And indeed, if you look at how you apply this theorem into hardness of approximation, oftentimes you would like this number to be much, much smaller. Almost always you want it to be arbitrarily small constant, and in some cases you even want it to vanish with the instance size. So that's important. And another aspect where you can hope to improve is about the proof length or the witness length. So polynomial length is something that is nice, but if it's like 10 to the 100, it is polynomial, but you can try to get something better. So can we get shorter PCPs? And as I mentioned, these are aspects that you care about PCP, inherently about PCPs, but getting better results here has applications to other areas, such as optimization, as I said, hard approximation, verification, complexity in general, and crypto. And each one of these things cares about different regimes, different parameters, but it's all in there in one way or another. I mean, we'll see some applications, and you'll see some of it. Okay. So is everybody clear on how are we going to try to improve the PCP theorem? Cool. Okay, so of course, these are natural questions, and many, many works have been done about these things. So let me mention some of them. So the first way to improve the soundness of the PCP theorem was established by the parallel repetition theorem of Ram, who showed that indeed you can drive this 0.99 number to arbitrarily small constant. Hey, Mark. And this is a very nice theorem and a very nice technique, and all of it is very, very nice. And there have been several subsequent improvements. And I think that it's fair to say, and people in the audience would probably agree with me to an extent, that parallel repetition is well understood in this context. So good. So that gives you soundness which is arbitrarily small, but sometimes you want to get soundness which is vanishing with the instance size. Let's say 1 over log n or 1 over log n, something like that. So that also exists. There are many details here that I'm omitting, but if you're willing to pair in some other aspects of the PCP, namely the number of queries it makes, this is something that has been known for a long time. But if you really care about 2-query PCPs, then this is substantially harder. And this was done first by Moshkovitz and Raz. And following that, there have been other ways to do it. But again, this is serious stuff. Cool. So as far as soundness is concerned, we do know how to get small soundness. So now let me talk about the length of PCPs. So the first work addressing this length issue was by Polisuk and Spillman, who roughly speaking showed that you can get a PCP of size almost linear, in the sense of n to the 1 plus epsilon, but the soundness is again some 0.99 business. So now there is this work, very nice work of Ben Sasson and Sudan, who showed how to get quasi-linear PCP. And when I say quasi-linear, I'm always going to mean n times polylog n. So that's almost as short as the original proof itself. But the soundness wasn't that great. It was 1 minus 1 over polylog. So not as bad as the trivial verifier that just sample the clause, but still the soundness is close to 1. And following that, Dinu in 2007, and building on this Ben Sasson Sudan work, showed how you can get the same size PCP, but soundness which is bounded away from 1. So she was the first to get quasi-linear PCP with soundness which is bounded away from 1. Okay. Cool. Nice. And the one last result that I want to mention, which is a little bit incomparable to the result of Dinu, is that you can ask, okay, what happens in Dinu? Why do you get stuck at this 0.99? And the answer is that we'll talk about it. But if you do want to go to small soundness, then actually the result of Moshkovitz and Raz from above gives you size which is still quite small, n times 2 to the square root of log n, but their soundness is vanishing, actually with n, but let's call it epsilon. Okay. So as far as this light is concerned, the situation is if you want quasi-linear size, then the soundness you can get is a little bit bounded away from 1. And if you're willing to go slightly higher in size, then you can drive the soundness all the way to 0. Okay. Yeah. So with the exception of Poiseuille-Spillman, they are all two-query results. I think that even this one is 2 queries. There is some funny trade-off. I mean, what I'm saying here of these 2 epsilons are maybe not the same, is what I'm saying. Cool. Any more questions? Nice. Okay, so let me tell you a little bit more about parallel repetition, just to see what it gives you and what it doesn't give you. So here is the mindset that you should have. So we have this PCP theorem. It gives you this verifier, which is very cool. It has soundness which is bounded away from 1, and now we want to amplify this verifier. We want to build a verifier that has much smaller soundness. So the most natural thing would be just run the verifier k times. Run it, accept or reject, run it again, accept or reject. But this is undesirable for us because in PCP language, that would amount to making more than 2 queries. Each run of the verifier is 2 more queries. And I'm not going to have time to explain why, but at least as far as hardness of approximation is concerned, getting 2 queries is really important. Like if you get more than 2 queries, it's very nice, but it has much less applications. So doing this naive sequential repetition works trivially. It decreases the soundness, but it increases the number of queries. So how do we do this sort of idea without increasing the number of queries? So you just do it in parallel. So what do I mean by that? So let's say that we have the verifier VPCP. It has access to some witness, which is a string W1 to WM. Now I want to simulate a verifier that makes k checks of VPCP. So what I'm going to do is I'm going to consider this VPCP tensor k. This is the notation I'm going to use, which has much longer proof. But each location in that proof would relate to k locations in the original proof. So I sort of squeeze the k symbols from the original proof to that. These k symbols correspond to what would VPCP read when you do it k times. And that's how you do parallel repetition. Okay, in slightly weird way, but it's really what you do. Okay. So this is what parallel repetition is. And let's make one observation, or let's start with one observation. So the first observation, or one observation, is that if the length of the original witness is m, and for any k locations in it, I have a location in W prime, then the length of W prime is m to the k. So the proof size increases by polynomial in k. So it's like even if I do 10 repetitions, it already go from n to the 10. So these sort of ideas cannot give you short PCPs. But the good thing about them is that we do know that they decrease soundness, and this is the parallel repetition theorem. And it's the following result. So given this VPCP, if phi satisfiable, then the tensored verifier accepts for BT1. And if not, it accepts the probability which is exponentially small in K. Okay. So if you haven't seen this theorem ever, you might think that it's trivial because it's independent runs. And it's a funny story. And some people also thought that and wrote it in their paper, but this is a serious theorem. It's quite hard, but it is true. So the amplification aspect of this theorem is great. The soundness goes down exponentially small in K. But the primary issue here, with respect to what we discussed, is that the size of the proof increases considerably. It increases from size m to size roughly m to the k. In particular, anything along these lines cannot give you near linear PCPs, let alone n times polylog. And secondary issue is that each symbol here now includes k symbols from the original one. So if your alphabet was sigma, the new alphabet is going to be sigma to the k, which is again much, much larger. And if you squint at this alphabet that you get versus the soundness, you'll realize that the soundness of the eventual PCP is something like 1 over alphabet size to some number strictly bigger than 1. But it's a number which is not really explicit. I just made it up. Okay. So can we fix these two issues about parallel repetition? So question number 1, how can we do soundness amplification with more modest blow up in the size of the PCP? Ideally, we would like to keep it linear, but life is far from ideal, so maybe like a quasi-linear size. And secondly, we can hope to get the best trade-off between the alphabet that we get in the construction and the soundness. So it's easy to see that if your verifier reads 2 symbols from a string over alphabet Q, regardless of if phi is satisfiable or not, it's going to accept with probability at least 1 over Q. Because if you just sample this string at random, this will happen. So you cannot drive the soundness to be smaller than 1 over Q, but can you get to it? Okay. So now we get to the main results that I'm telling you about in this talk. So with respect to the first question, can you amplify with less blow-up? The answer is yes. So this is theorem 1. It's based on a sequence of works together with Mitali, Nikhil, and Noam. And some of these works have been proven independently by Dix and Dinur and Lubotsky. So theorem 1 says that there exists a PCP construction with size quasi-linear that has small soundness, arbitrarily small constant. And as I said, I'm not going to give you all of the proof, but let me give you some buzzwords, and I'm going to tell you a little bit about some of these buzzwords. So the proof relies on this new cool thing called high-dimensional expanders, direct product testing, distributed computing, some regularity business, some combinatorics. Then one thing that I'm not an expert, so if you have any questions about it, don't ask me. It relies on some algebra, in particular some quaternions and periodic numbers. It's some cool stuff. Also graph products, and again, you have to know some group theory, which I don't. Yeah, so these are the tools that go into this proof. And I'm going to tell you a little bit about some of them. So now with respect to the second question, suppose the alphabet size is Q, what is the best soundness that you can get? So we have the following result with chi, and we show that for any Q, there is a 2 query PCP construction where the completeness is close to 1, it's 1 minus little of 1, and the soundness is almost 1 over q. It's 1 over q to the 1 minus a little of 1. And because it comes up in some applications, I've also spelled out what is the size of the PCP as a function of the alphabet size. It plays a role in one application, and it's fairly decent. It's not too bad. Okay, so these are the main results. Let me pause to see if there are any questions. Painful. So I wrote here a polylog with typos. So it's log to the power c, where c depends on epsilon. And in fact, probably I don't know how to tell you what is the dependency, but I would guess it's a couple of exponential in 1 over epsilon. Good. More questions? Cool. Okay, I forgot to tell you. So this second theorem uses, there is some intersection in the techniques, but this is more Fourier analytic, but we still use direct product testing and some other nice stuff. Okay. So in the rest of the talk, I had to choose what to tell you. So I'm going to tell you a little bit about what's going on in theorem 1. And in particular, I'm going to tell you, okay, so before that, I'm going to tell you about applications. That's important. So I did promise to you that each one of these parameters plays a role in different applications. So let me demonstrate it. So this is theorem 1, and here are some applications. So first, we get better hardness of approximation results, assuming the exponential time of processes. Here is one example. So suppose I give you a formula phi, then there is no algorithm that runs in time 2 to the n over polylog n that distinguishes between the case that phi is fully satisfiable and phi is at most 7 over 8 plus a little bit satisfiable. So without this time lower bound, this is a classical result of Hastad. And the new content here is that assuming ETH, there is not an algorithm which is barely sub-exponential for this seemingly much easier task. So using Hastad 2 to the n to the epsilon, but using Moshkovitz-Raz 2 to the n over 2 to the square root of log n. Yeah. Cool. And the second result, which I'm not actually going to tell you what it is, I'm just going to write some words, but I'll give you a feeling to what it is really. So it's not really a consequence of the theorem, but rather of the techniques. So we show that you can generate a graph that has polylogarithmic degree that has very efficient routing protocols that are tolerant against edge corruptions. So don't worry if none of these words make any sense. I'm going to explain them a little bit better, but for now, think about it is you have some distributed network, some vertices want to send messages to other ones, and they do it via the graph, but some of the edges don't work. How can you do that reliably? That's kind of what you want to do. Cool. Okay. Now applications for the second theorem. So first of all, it gives a near optimal trade-off between the soundness and the alphabet. And this improves upon two previous results, one by Cotton Safra, who got 1 versus 1 over q to the 1/6, and some very nice work of Sion Chan, who got 1 versus log q over square root of q. Sorry? I think that I'm citing the journal version. Yeah. Yeah, maybe that's a bad. I never know whether to cite the archive version, stock version, or journal. Yeah. And it's certainly the case that Chan is a little bit after that work. Yeah. Okay. So the second result, which was actually for me the primary motivation, is about quadratic programming. So I give you a quadratic form of this type. So q of x equals aij times xi times xj. And I ask you to find the maximum over q over the Boolean cube. Then there is a classical algorithm based on SDP that gets an off log n approximation. And using this reduction of Roa et al. And this result of Cotton Safra, they show that it's quasi-NP-hard to get log n to the 1/6 approximation. And when I say quasi-NP-hard, I mean under quasi-polynomial time reductions. And using this new theorem, we can get almost log n hardness against quasi-NP. Yeah, so this is almost tight. No. So this is the reason that I'm mentioning the size. So for this result, it's actually important to take q, which is large power of log n. So here you'd get, yeah. So Chan has n to the 2 to the q instance size because he's using the long code, and it's painful. Yeah, but it's a good point. Yeah. So for this result, you really want good dependency of the size on the alphabet size. Mm-hmm.
So is there a certain application you can obtain for approximating the advantage over random for let's say PSAT? So imagine that the completeness is 7/8 plus epsilon.
Mm-hmm.
And I want to understand what's the best possible numbers I can get from 7/8 plus delta. And what I'm interested in is the ratio epsilon over delta.
I'm not sure. Okay. I have an immediate objection that the Hassad reduction uses long code. So it's going to be more painful in terms of the alphabet size. But I would have to think about it if it gives anything. Cool. Good question. The answer is that after that, I thought that there is a connection. The connection is that after this work, we thought that there is a connection. We looked into it. Then we sort of discarded it. My honest answer is that there may be a connection and there may not be a connection. I don't know at this point. Yeah. Yeah, but there are some reasons here that like even if you're willing to do some slightly super polynomial things, there are reasons here that you cannot push Q to be beyond log n. Yeah. So yeah, it's not completely clear in my mind. This is the honest answer, but it's not obvious also. Cool. And the third application I'm just going to mention, it's a collection of results based on this paper for some connectivity problems. Let me just tell you one of them. I'm not even going to tell the result, just what the problem is. So the input is a weighted graph G, some vertex R, and a set of terminals T. And you want to find the smallest subgraph, meaning the cheapest, so that for every terminal in T, there are at least k vertex disjoint paths from R to T. So you are trying to optimize the cost of this G prime, and using this type of result, you can show some hardness of approximation result for this type of problem. Okay. Cool. So now that we are well motivated by some applications, let me tell you about some of the tools in the proofs. And for sake of concreteness, I'm only going to discuss theorem 1. And in all honesty, I'm not going to say too much about it. If you want to hear more, my co-author Mitali is going to give a talk about it in the IS in a couple of weeks, and she will say much more than I can. But nevertheless, let me say some words, and I'm going to tell you, first of all, about this problem of direct product testing. So this problem has its origin in a paper of Goldreich and Safra, who attempted to simplify some parts of the proof of the PCB theorem. And let me state it without the connection to PCB, just it's an interesting problem by its own. So we have a function from 1 to n to sigma, and we want to encode it using what I'm going to refer to as the direct product encoding. So this encoding for each subset of k elements in n choose k assigns k symbols from sigma, and it just does so in the most obvious way. Given the set a1 to ak, I just assign to it the vector what f assigns to a1, what f assigns to ak. That's the direct product encoding. Now, as is the case oftentimes in property testing and PCPs, you want to be able to test whether a given encoding is actually a direct product encoding or not. So the testing problem is as follows. I give you a table G, which is supposedly a direct product encoding of some function little f, and your task is to test locally whether that's the case or not. So again, I want to test whether this G comes from some little f or not. So here is, okay, so this is a very interesting problem, and there has been a lot of research about it. Here are some references. But here is the test, which is really, really natural. You sample two k sets, A and A prime, that have an intersection of size, let's say, root k. So if this table came from some little f, then the shared elements surely have the same value. So this is what you test. You look at what G gives to A, what G gives to A prime, and you check that these two vectors agree on the shared elements. Okay, that's the test. That's what I'm going to refer to as the direct product test. So it's clear that if you run this test on a legitimate direct product encoding, it's going to accept with probability 1, because it just comes from the same function little f. And the really interesting question here is about the inverse type theorems. Suppose I give you a table G that passes this test with some noticeable probability. Let's say at least delta, or delta is some like 0.01 or something like that. Can you tell me that G comes from little f in any way? So here is a theorem by Dor and Goldenberg that show that yes, indeed, you can show that. So they prove that there exists some function little f such that G assigns to many of the k sets the same value as f would assign to them. And when I say many, I mean poly delta fraction of the sets. So for the experts in the audience, I'm slightly lying here, but it's fine, don't worry about it. Morally speaking, this is what they proved. If you pass the test with noticeable probability delta, then you're correlated with some legitimate direct product thing. And this is a really, really nice result. And as a paper by Impalacio, Kamenetz, and Wigderson showed, you can take this theorem as is and use it to amplify PCPs. And there is one slight catch here, which is the size of this direct product encoding is the size of the original little f to the power k. So again, your witness goes up polynomially, just like in parallel repetition. And this is not a coincidence. If you think about it, it's kind of like parallel repetition. In fact, sometimes it's referred to as the combinatorial analog of parallel repetition. Okay. So now we get to the question. Are there sparse versions of this encoding that take less than blow up to the k size? So I'm skipping a lot of works, but fast forwarding to 2017, where Dinur and Kaufman showed that if you look at high-dimensional expanders, then they do form sparse direct product. They can be used for sparse direct product tests, but only in the case that delta is close to 1. In the case that delta is, let's say, 1 minus epsilon, or let's say 0.99. And in the same paper, they conjectured that there should be some high-dimensional expanders that also support this business for arbitrarily small delta. And in down-to-earth terms, what sparse direct product tests really amount to is a clever choice of k sets of n. And sparse just means that the size is O of n, as long as you think of k as constant. And once you have this set, you can think about the direct analog of the encoding and of the test. It's on the slide, but I'm not going to say too much about it. Okay. So this conjecture was proved recently independently, as I said, by Vitali, myself, and Lifshitz, and also by Dixon, Dinur, and Lubotsky. And this builds on return on many, many other works in this really fantastic area. And so we do know that for any delta, any arbitrary small delta, you can cook up some clever choice of S where it works. Cool. So that's what I wanted to say about direct product testing. And now I'm going to shift to something which is related in a sense that I'll say in the end, but seems completely unrelated also at the same time. And this is the connection to distributed computing. So here is again an independent problem of interest, which you can think about, and people have done so indeed. This is routing in graphs. So let's say that we have a graph G. G equals VE, and it looks like that. And we're given a collection of source and sink pairs, S1, T1 up to SMTM. So these are linearly many pairs. And the setting is that SI has a message that they really want to send to TI, but they are not allowed to, just send it to them. They are only allowed to use edges of the graph to communicate messages until it reaches TI. So this is what the word routing refers to. You're trying to route messages on the graph. Okay, so we say that the graph G admits an R-round protocol if there is a protocol that succeeds in an R time to pass all of the messages from each SI to TI. And roughly speaking, the goal in this problem is to design a graph which is sparse, but at the same time, it admits good routing protocols. And when I say good, I mean that the time it takes this R is small, and also it has small congestion, meaning it's not that everybody sends their message to one vertex and it does all of the work and sends it to all of the rest. each vertex is supposed to send only kind of boundedly many bits. So a classical theorem from the 90s says that as long as G is an expander, you can indeed do it in off log n rounds. So that's very nice. And now we get to the setting which is more applicable to PCPs, which is the case where there are some corruptions.
How do you mean like the pattern is
Yeah. So you can think about it as each time step, some vertices send messages to their neighbors, and then the next time step, these neighbors send another message, and so on. So it's really the path length. Yeah. Okay. So what is fault-tolerant routing? It's the same problem, except that now we have corruptions. So the model of the vertex corruptions means that some adversary controls some small constant fraction of the vertices. They're able to control all of the messages that they send, but the protocol is still supposed to work nevertheless. And this problem has been considered since the 80s, and it is known that there are graphs with polylogarithmic degree and polylogarithmic work complexity which achieve that. And this notion of work complexity is sort of what I referred to earlier as the congestion. This is the total number of computation that each vertex makes throughout the protocol. So you want it to be polylogarithmic. Cool. So this is very nice, but unfortunately, this is not really what we want in PCPs. In PCPs, it turns out that the more relevant model is the edge corruption model, which is more general. So in this model, instead of the adversary controlling a small constant fraction of the vertices, they get to control a small constant fraction of the edges. So this is clearly more power, because if an adversary wants to say, oh, I'm controlling V, he has control of the outgoing edges of it. But I can sort of control half of V and half of W, so it's more tricky. And again, the goal here is to design sparse networks. So this model somehow has only been considered in very few works. And the one work where they get the best results that I know of has parameters which are too weak for us. I'm not going to spell out exactly what they are, but sort of they're not able to handle constant fraction of corruptions, but rather like 1 over log n fraction of corruptions. So what we do in this final paper is that we show that there are graphs with polylog degrees that achieve fault-tolerant routing with work complexity, which is also polylogarithmic. And I couldn't write to the graph here. It's some HDX thing, which is, again, fairly complicated. Not really. I mean, there is some absolute thing, because we can only handle up to some epsilon naught errors. Beyond that, even increasing the polylog won't help. Yeah. Cool. So just to finish this argument, so for this theorem 1, we make these 2 requirements. We need a good direct product tester, which again amounts to construction of some graph with some nice properties. We need, again, a graph which has good routing properties. And as it turns out, we want these 2 properties from the same graph. And somewhat luckily, I only know of one example for a graph for 1, maybe 2. I mean, probably there are more, but as far as we know, there is only kind of 1 known construction. And again, I know of only 1 construction that has good routing. And luckily enough, it's the same one. So we use that. And this is a main component in our proof. And again, I wish I could tell you exactly what this object is, but it's some periodic stuff. Okay. And actually, so we're not the ones to come up with this construction. There is a nice paper of Michael Chapman and Alex Lubotsky, which originally suggests it's, for somebody who is a group theorist, I think that it's a natural extension of the LSB complexes. But for the rest of us, for me, for example, it's some bizarre object, which is very interesting. Okay. So let me conclude with some remarks and open problems. So I told you about two results. One of them is alphabet soundness trade-off for PCPs. Another one is small PCPs with small soundness. And I try to tell you some connections to other things, such as direct product testing and distributed computing. As open problems, can we get linear size PCPs? Actually, it's not even clear what I mean here. There are some issues here. There are some logs which you cannot afford not to lose, but that's a separate issue. And sort of my belief is that once there is one application, there should be more than one. So this is the first application of HDX in PCPs. And are there any other ones? And are there any other applications of our routing idea? I don't know. General philosophy is that, as far as I see it right now, what HDX are able to offer you is some very sparse structure, which nevertheless is highly connected. So far the same could be said about regular expander graphs, and it's true. But in one word, what HDX buys you is that it has very large cliques, which is the best connection you can hope for. And these cliques, if you think about them as coalitions and you try to do some error correction using them, then you start running into distributed computing and how to combat corruptions, which is actually what we do. So this is very helpful for us, and I think this should be helpful in other ways, but let me stop here. So that's all I have to say. Thank you.